Okay, thank you everyone for joining in today for this talk. It is really a pleasure to speak with you all. I would start this presentation with a bit of introduction about myself. I am Sumit Arora. I am currently working as a senior research scientist in the modeling and simulation group in Simcyp. And I have been extensively involved in the development of new models in the oral and dermal module of Simcyp. In today's presentation, I'm going to talk about the thought process behind the development of mechanistic absorption and disposition model of ritonavir. Uh, Let me just get the pointer here. Yeah. So the outline of my presentation would be like I would be discussing briefly about the aim of the current work, a bit about the background and the challenges which were there in developing a compound file for ritonavir. We followed a model qualification or disqualification approach, which we did in a stepwise manner, and we're gonna go through all the steps. We'll have a discussion about the results and what are the mechanistic basis of the results which we observed. And finally, we'll have some conclusions, and we also discuss some of the limitations of the current model. So the objective of this research is to develop a mechanistic absorption and disposition model of ritonavir, which could link the biopharmaceutic properties of the drug and the drug product with its DDI risk potential. This is actually one of the very few examples where the formulation characteristics of a perpetuator drug has been included for assessment of its DDI risk potential. And as you can imagine, formulation has a huge impact on the rate and the extent of drug delivery, uh, which can has an impact on drug absorption and therefore the level of DDIs. So the major point which I want to make here is that it is really useful to develop one model where you can combine both the biopharmaceutic properties as well as the DDI parameters and can really then understand the entire how the model is performing, and then it's really kind of a very powerful model then and quite robust because you are also including formulation characteristics while assessing the DDI risk potential. Sorry, I forgot just few housekeeping rules. I should have mentioned it at the start of the presentation. So if you have any questions, please write it in the chat or you can ask at the end of the presentation. So you can raise a hand or unmute yourself and please feel free to ask any question. So the running theme for today's presentation is biopharmaceutics in vitro in vivo extrapolation. So one of the major objective of the Orbiter project, which was a very big project funded by European Union, under that project, one of the major aim is to develop novel in vitro biopharmaceutic tools, which can enhance our understanding and can help us to relate biopharmaceutic properties of drug and the drug product with the clinical observations. So a lot of number of tools were investigated and developed under Orbito, and these tools are really fantastic because they really help us understand how the drug behavior or dissolution in vitro can be related with in vivo. However, most of these tools only gives us a relationship with the mean profile, which can be observed in an average individual or a population representative. These tools does not really tell us about the variability of the exposure which is expected in an in vivo scenario in a wide population. So with biopharmaceutics in vitro in vivo extrapolation, we mean that we understand our in vitro systems, we know all the experimental conditions under which the in vitro data is generated. We should use that data in order to verify the key parameters of our API and the drug products, which are important for absorption of the compound in vivo. So in this case, if we know the solubility of a compound in aqueous and in biorelevant media, we can understand with that information the intrinsic solubility of the molecule. We can understand the pKa and the solubility factors. So we need to understand and model these in vitro biopharmaceutic experiments in order to gain confidence in the input parameters of the drug and the drug product. And once we have gained an understanding of these input parameters, we can put those input parameters within a PBPK model where we can then combine them with the population variability which the PBPK models provides, and can then understand the variability which is observed in an in vivo scenario. So the running theme of today's presentations would be based on biopharmaceutics IVIVE and how we used this biopharmaceutics IVIVE to parameterize the absorption model of ritonavir. Uh, these are some of the case examples which we have published over the years. Most of them are weak bases. Because of their complex nature, they have a tendency to precipitate when they transfer from acidic to the basic media. And please have a look at these papers if it is of interest to you. So let's start with the challenges of developing the PBPK model for ritonavir. Ritonavir has a complex pharmacokinetic profile. It's a very complex molecule. It has a number of mechanisms which defines the disposition of this compound in vivo. It is a mechanism-based inhibitor of CYP3A4 and 3A5. Simultaneously, it is also an inducer of CYP3A4 and 3A5. It is a PGP substrate as well as its inhibitor. It is also has a competitive inhibition mechanism for CYP3A4 and 5. So it has a lot of things going on. Secondly, as it is quite often we encounter this situation, there is a lack of intravenous data for this compound in literature. So we really don't know the intravenous profile. And whenever we are developing a mechanistic absorption model where we don't know the where we don't have the intravenous plasma concentration time profile, we always run into parameter identifiability issues. And we're going to talk about these things, that in cases where we don't know the intravenous profile, how we can navigate so that we reduces the parameter identifiability issues. We also didn't have any information about the fraction metabolized of ritonavir by CYP3A4. So this is another an important piece of information missing. The commercial formulation of ritonavir is an amorphous solid dispersion. Amorphous solid dispersions are quite complex products. The dissolution of amorphous solid dispersion under non-stick conditions can be quite complex because it has a possibility of several phase transformations. Not only when the ASD is dissolving within the dissolving media, but crystallization can also happens in amorphous solid dispersions when they are at storage. So these are thermodynamically unstable systems, and therefore there are chances that the drug can crystallize back to its original polymorph, or it can even crystallize to a different polymorph. So a lot can happen, and we really need to understand what's going on with ritonavir commercial formulation. Finally, being a weak base, it has a tendency to get dissolved in the acidic media really rapidly. And then when it is transferred from the acidic stomach conditions to the basic small intestine conditions, there are chances that the molecule can precipitate. And therefore, we need an understanding that how we can parameterize models which can capture this interplay between supersaturation and precipitation. So there were quite some challenges while developing the compound file for ritonavir. We adopted a model qualification disqualification approach in a stepwise manner until consistency with the clinical data is obtained. So the first question which we asked while getting on with this project is, can we simulate ritonavir in its amorphous state? So Norvir, which is the brand name for ritonavir commercial formulation, it's a 100 milligram tablet. It's an amorphous solid dispersion with ritonavir with copovidone. It's a 15% drug load. Sorry. The glass transition temperature of ritonavir is around 50 degrees centigrades, which shows that the molecule has some inherent stability at room temperature. According to the classification which is published by Bruno Hancock from Pfizer, ritonavir could be classified as a drug with low propensity for crystallization. So the molecular weight of this compound is around 721 Daltons, and it has 18 rotable bonds. So it's a quite a big and a bulky molecule, and its propensity to crystallize is quite low. Finally, there is an interesting piece of research which was done from Professor Lynn Taylor's group from University of Purdue, and they found out that the nucleation induction time, so the nucleation induction time is usually the time taken to reduce the initial supersaturation concentrations by 2.5. And it is kind of an indication of the stability of the amorphous form in a particular media. So for ritonavir, the nucleation induction time was found to be around 700 minutes in composite simulated intestinal fluid. With composite simultaneously in simulated intestinal fluid, I mean that they have added some more bile salts into the classical FAST media in order to make that more biorelevant and comparable with the human intestinal fluid. So in composite simulated intestinal fluid, it was around 700 minutes, whereas it was around 300 minutes in fasted state intestinal fluid version 1. So if you look at even the nucleation induction time in fasted state intestinal fluid version 1, which is around 300 minutes, so this is roughly 5 hours. And what we have in Simcyp as a mean residence time in small intestine is around 3.3 hours. So if the molecule is staying as it's at its amorphous form for nearly 5 hours, that's quite a significant time for a molecule to get absorbed from the gastrointestinal tract. So while doing the simulations for ritonavir, one of the major assumptions which we made is that it is quite likely that the molecule remains in its amorphous state during its transit in gut. And there are some in vitro dissolution data as well, which is support this hypothesis. So we used advanced dissolution, absorption, and metabolism model in Simcyp for modeling the mechanistic absorption of ritonavir. I'm sure most of you are familiar with ADAM model. Briefly, the gastrointestinal tract in ADAM model is divided into 9 anatomical sections. So we have stomach, a duodenum, 2 jejunum sections, 4 ileum, and a colon. And the release of and the drug is absorbed from each of these compartments as a function of. So this is a unit cell of the drug release, which is happening in the gastrointestinal tract. So the drug first needs to be released from the dosage form. It then needs to be dissolved. Once it is dissolved, based on its conditions in the lumen, so based on the concentration of the drug in the bulk lumen, it can either supersaturate or it can precipitate. The drug is also subjected to degradation. The drug can absorb. It is also can be metabolized, or it can be also taken up by the transporters or effluxed by the transporters. Once the drugs gets into the portal vein, it goes to the liver. It can be first pass metabolized, and then it can be linked with a minimal PBPK or a whole body PBPK model. Also, the drug is actually transiting between one compartment to another compartment. The drug and the fluid both actually are transiting from one compartment to the another compartment with the use of a first order transit constants. So on the right, this is the absorption rate from the nth atom segment, and this is the equation which we use to model this. So on the left, the differential term includes the concentration of the dissolved drug in the gut lumen of a particular nth segment. A total is the total amount dissolved, and 2 by R into PEF is nothing but an absorption rate constant, which is Ka. So 2 by R is the surface area to volume ratio, and PEF is the effective permeability of ritonavir in a particular nth segment. So this is the basic equation of the absorption rate from the atom. So prior to version 18, we only had mass balance only model, but from version 18 onwards, we now have 2 ways of handling dissolution of particles within Simcyp. So initially, the model which we had was mass balance only model. And with this model, what we track is only the mass of the drug which is getting dissolved or transiting or absorbed. So it is only tracking the mass of the drug. So, and also in this model, the number of particles were always constant. So in this model, there is no particle birth or particle death happening. The number of particles were always constant. And as you can imagine that this is not a real situation. If you have a particle and it is dissolving, it should disappear at some point, or if precipitation is happening, the new particle should form. But in mass balance only model, because of the structure of the model, we have the constant number of particles, and this can sometimes lead to overestimation of the simulated dissolution rate. So you are actually dissolving much more than what you should actually see. So this was a bit unrealistic. So from version 18, we have implemented the particle population balance model. It is much more mechanistic. It has much more features to consider. And the major point of this model is that we can now track both the mass of the drug which is dissolving, transiting, or absorbed, as well as the particle count. So we can track the number of particles which are transiting from one segment of the atom to the another segment. The main idea is to track the number of particles, and these are the equations. I'm not going to go in detail of these equations, but what I'm going to briefly mention is this G term. The G term can either be a dissolution or a growth function, depending upon the concentrations which a drug encounters in the bulk media. So if the concentration of the drug in the lumen is less than the saturation solubility of the drug, then you will have dissolution, so the drug will dissolve. But if the concentration of the drug in the bulk medium is more than the saturation solubility of the drug, this term will become positive and you can actually start growing the particles. So in this case, you can see that the same equation can be used to model dissolution as well as growth. However, for nucleations, for formation of new particles, we need another model, which is the classical nucleation theory being implemented in Simcyp. So we can use that to model precipitation now, in addition to the empirical models. And of course, it also transits the number of particles which are moving along the gut. So the main idea here is to the summary from this slide is that the main idea is that we track the particles, so we know that how many particles are there in the simulations. We understand, and also we can now model the particle dissolution very well, which is in a more realistic manner. And also we consider particle birth as well as particle death, which is closer to the real situation. So just to provide a brief comparison between the main functionalities of mass balance only model versus particle population balance model. So we talked about this particle death and a birth, which can be then considered in a PPV model. This is more realistic situation. The particle size bins can be easily handled, so there are more flexibility in this. And two of the main things which I wanted to mention here is that with particle population balance model, you now have the ability to model two solid states. And with two solid state, I mean that if in a product, for instance, if in an amorphous solid dispersion, you may have some crystallization happening. So you may have two moieties like the amorphous and the crystalline. So you can use that, you can use this model to model both the crystalline as well as the amorphous part simultaneously. So you can model two solid states with particle population balance. Plus the model also allows us to define a food staggering model. And with this, what I mean is that you can now actually define the entire clinical trial. So you can really define that at what time a meal is given to the patient or a drink is given to the patient. So for instance, the meal is given at 4 hours, the drink is given at 6 hours. And if you really wanted to investigate the impact of this intermittent giving of meal and fluid on the drug pharmacokinetics, you can actually simulate that. You can define the entire clinical trial within the model. So this is actually quite a very useful implementation in Simcyp, which we had from version 18 now. And it really has enhanced the capabilities of ADAM model. Global sensitivity analysis is another powerful implementation, and it is introduced in version 19 last year. And the main idea of the global sensitivity analysis is to analyze any interactions which are happening in the sensitivity analysis. So with interaction in sensitivity analysis, I mean that the model output for a particular parameter can change depending upon the value which is assigned to another parameter. So if two parameters are interacting, it is possible that your sensitivity can change when the value of the other parameter can change. So global sensitivity analysis takes into account simultaneous parameter variations over large ranges, and it gives us a rank order of the number of factors which can be important in the simulation. So prior to starting the work for development of model for Ritonavir, we selected most of the relevant parameters, which we believe that has an influence on the absorption of ritonavir from gut. And what we find out that the parameters such as the particle size, the intrinsic solubility of the amorphous form, and the release of the drug from the dosage form are kind of most important, are kind of the most important parameters which were having an influence on the absorption of ritonavir from Adam. And this is quite useful to know in the start of the model building, because then you can focus more on these sensitive parameters, and you can make sure that you gain sufficient confidence in the parameterization of these input parameters. So now I'm going to go through the thought process about this sequential modeling of in vitro biopharmaceutics experiments. So how we did the sequential modeling to parameterize the key parameters in the ADAM model. So we first start with understanding the aqueous solubility of the molecule. We then moved to understanding the biorelevant solubility. Once we understood the solubility and we confirmed some of the factors, we then went on to model the dissolution to understand whether we can predict the dissolution bottom up or is something we are missing in dissolution. And then we went on to model the PS shift experiments to understand the precipitation and supersaturation behavior of ritonavir. So SIVA-3 was used in this work for modeling the in vitro biopharmaceutics experiments. And this is kind of like a confirm and a learn approach. So you try to model your in vitro experiments. If it can capture your in vitro experiments, well and good. So you confirm your parameters. But if you don't capture your in vitro experiments, you can optimize or fit certain parameters. So you can learn from them, fit certain parameters, and then try to see whether you can explain those fitted parameters with an external data set. So you can use an external data set as a verification. So let's start with understanding of the aqueous and biorelevant solubility for ritonavir. This is the global solubility equation, which is implemented in Simcyp and in SIVA. And it helps us to mechanistically model different components which are contributing to the total solubility. So it helps us to understand that how much of the component of the total solubility is coming from aqueous phase, how much coming in the presence of bile. So if there are bile salts and we see a solubility enhancement, what component of that is coming from the biles? And you can also now start it to understand that if an excipient has an impact on the solubility of your API. This model was developed for excipient, particularly keeping cyclodextrins in mind because they are the known solubility enhancers. But the model can also be used to understand any solubility enhancement which can happen in the presence of polymers. You can actually break down your entire solubility into different components, and it is quite useful. So if you don't active your bile micelle mediated solubility enhancement, so if this portion is not active, the equation reduces to this one. And this is basically the solubility which is coming from the neutral form and the solubility which is coming from the ionized form. And for calculation of the ionized form, it simply follows Henderson-Hasselbalch equation. And depending upon the compound type, you can predict the fraction of solubility which is coming from the ionized form. And here you try to understand how much of your compound is going to the bile by determining the partitioning coefficient of the neutral species from micelles to water, and this is the partition coefficient from the neutral species from water to micelles, bile micelles. Okay, so we started with understanding the aqueous solubility for ritonavir. Please remember here that we are simulating ritonavir in the amorphous form. So what we are interested here is to understand that the free base amorphous solubility of ritonavir. And we found that Zhu et al. In 2017, they published a paper, very interesting paper actually. And they found that the amorphous solubility of ritonavir is around 38.5 microgram per ml. And we also find out that the solubility of ritonavir in 0.1 normal HCl was around 4 milligram per ml. So usually solubility of a weak base in the acidic pH is limited by the formation of its salt. And there are two ways where we can use the in vitro data to understand this salt-limited solubility of weak bases. The first can be the solubility factor. Solubility factor is nothing but simply a ratio of the observed solubility divided by the intrinsic solubility. So if you divide 4 milligram by 38.5 microgram, you'll get this factor. So with solubility ratio, what we are doing is we are just capping the solubility of weak base in the acidic range. And another way to do this in a more mechanistic sense is to understand the solubility product of the salt of the weak base in the acidic pH. So if we know the KSP of the weak base of the salt which has been forming, we can tend to mechanistically understand this plateauing of the solubility which is happening in the acidic pH. And in Simcyp, you can now do that. So if you know the KSP of the salt, you can input that. And with KSP model, you have an advantage because that model takes into account also the common ion effect. So for a weak base like haloperidol, it was observed that as you are going more into the acidic pH, the solubility after reaching the plateau phase actually starts going down. And this is because of the common ion effect exerted by the chloride ions. So the KSP models can take into account of that, whereas the solubility factor model just keeps your drug at the plateau range. It does not really take into account this decrease in the solubility, which one can observe because of common ion effect. So we note these values and we fitted the solubility factor, and with this we confirmed the intrinsic solubility, so this free base amorphous solubility, the PK of the compound, and the solubility factors. And we know that from some of the research which is again published from Professor Taylor's group from University of Purdue, that the amorphous solubility also follows the Henderson-Hasselbalch equation. We wanted to understand this bile-mediated component, and for this we had some of the data from literature. So we have the data from fasted intestinal fluid version 2 and fed intestinal version 2. And we know this data here. So what we did is we tried to fit this partition coefficient of the drug of the neutral species from water to bile micelles and for the ionic species. But as you can imagine, ritonavir is a weak base. It is usually non-ionized at this pH. So most of the contribution is the enhancement in solubility, which we observed 60 and 180 microgram per ml, is coming from the partitioning of the neutral species from water to the bile micelles. So it is usually the neutral species which was playing a role here in enhancing the solubility of ritonavir. So we fitted this parameter and we were able to explain the observed passive and passive solubility. So with this exercise, we confirmed the bile micelle partition coefficient, and this is quite important because this parameters are fitted considering 3 millimolar and 10 millimolar bile. But you can imagine now you have this partitioning component, And in vivo, your concentration of bile in subjects can vary very widely. So it can vary from 3 millimolar in fastage to 15 millimolar or maybe more. And you have this bile concentration term. So now when you add these parameters in an in vivo simulations, you can take the advantage of the in vivo variability, which is coming from different bile concentrations. But if you just put directly the value of FASIV and FASIV like 60 and 100 and directly into the software, you are using this variability. So you are using this component of variability which may come from different bile. So that's why we are breaking the solubility into its components, and then we are plugging back into the PBPK system where we are now taking advantage of the variability which is offered by the PBPK systems. And this is just to show you the data. So we were able to capture the pH at both pH 1, 7.4 in FASIV and FASIV. So now we know, we got some understanding how our solubilities are behaving in the aqueous and in the biorelevant media. So we are now moving to the dissolution and was trying to understand whether we can predict dissolution bottom up in vitro. This is the mechanistic dissolution model, which is the diffusion layer model implemented in SIVA and Simcyp. It is based on the equation which was given by Wang and Flanagan in 1999, and this is the equation which is being used currently in the model. The model assumes that the drug is dissolving from the entire surface area of that particle, and there is a non-linear diffusion coefficient, diffusion gradient in the hydrodynamic boundary layer. The main assumption of the model is that the rate limiting step is diffusion across the hydrodynamic boundary layer, which has an effective thickness of half. So in this particular model, we used Hint-Johnson model to calculate half. And this model assumes that if your particle size is greater than 30 micrometer, so your hef is equal to 30 micrometer. But as your particle size decreases below 30 micrometer, your hef is actually linearly related with your particle size. So as your particle is dissolving, your hef is also decreasing. So this is the equation. We had the general form of the dissolution rate equation. And you can see from this equation that the dissolution rate is dependent on the concentration gradient of the drug from the surface to the bulk. So we are assuming non-sync conditions because you have C bulk in the conditions. So if the concentration in the bulk is less than the surface solubility, the particles will start dissolving. But if the concentration is the bulk gets more than the surface solubility, this term will become negative and this then become positive, and the particles will actually start growing. So this is what we have in Simcyp and in SIVA. And we also have the scalar SDR, which gives us a bit more flexibility. And one of the example which I can give you where we can use this scalar is because the diffusion layer model assumes that the dissolving particles are spherical, but in reality, particles are all shapes and sizes. They can be needle, plate-like. So the effective surface area, which can be offered by these plate-like or needle-like morphologies, can be actually greater than the surface area which is being offered by the spherical particles. So if in your in vitro dissolution you are under predicting in the simulations, you can actually fit a scalar to take into account of this extra surface area. So this is one of the examples, but you can really use this for a lot more if you're not able to capture your dissolution profile in vitro. Another thing before moving on to the dissolution modeling I wanted to discuss is the release of drug from the amorphous solid dispersion. The release of drug from the amorphous solid dispersion is quite complex, and it can be either polymer controlled or it can be either drug controlled. So this is a graph which is published by Han et al. And it's quite a good description of what can be happening. So in a region of low drug loading, where there is a linear relationship between the drug loading and the percentage drug which is released from the ASD, you usually have a carrier controlled or a polymer controlled release, because at the lower loading you have low amount of drug. So in this, the yellow is the drug and the green is the polymer. So there is really low amount of drug which is uniformly distributed within the amorphous solid dispersion. And when the amorphous solid dispersion is dissolving, it is actually the polymer which is taking the drug along with it into the solution. So in this, usually for at a lower drug loading, you have polymer controlled dissolution, but at a certain point in a drug loading, you start see a deviation. So there is no more linearity between the drug loading and the percentage drug which is released in the medium. And at that range, you start seeing drug controlled release. And with this, why this is happening? Because now you have a lot of drug, because you have a higher drug loading, you have a lot of drug within the amorphous solid dispersion. And once this amorphous solid dispersion starts dissolving, so you put this amorphous solid dispersion in water. Sorry, is this somebody asking any question? Oh, please, can you mute yourself? Thank you. So when this amorphous solid dispersion is dissolving, the water can ingress within this amorphous solid dispersion. So it will increase the mobility of amorphous particles. And what can happen is that these amorphous particles can come together and can form amorphous domains. They can go to the surface of this dissolving amorphous solid dispersion, and therefore can result in a drug controlled dissolution. So they can actually lead to the surface enrichment by the drug of this dissolving particle. So at the surface, the entire surface is now covered by the drug, and therefore the dissolution becomes drug controlled. And interestingly, this is another piece of research, again from Professor Taylor's group from Purdue University. What they did is they prepared a series of ASDs with different drug loadings, and they measured both the release of drug and the polymer. So what they did is the red is the drug and the blue is the polymer, which is PBPK, copovidone, and also our commercial formulation is with copovidone. So you can see that from 10%, 20%, and 25%, the drug and the polymer are releasing at the same rate. But as you go to the region of higher drug loading to 30%, 35, 40, and up to 50, you start seeing a disparity between the release of the drug and the release of the polymer. And this is quite important to know, because virtually at 50% drug loading, your drug release is really less, and even your polymer release is suppressed. And this is because you have so much amount of drug, and when this ASD of 50% was put into the aqueous media, all of the drugs goes to the surface, and it also hinders the release of polymer from the amorphous solid dispersion. But our commercial formulation is 15% amorphous solid dispersion drug loading. So it lies somewhere in between these two, and we can assume that in that case, the release of the drug is governed by the polymer and not by the drug. So when we start modeling the in vitro dissolution experiment, we had some data. In simulated gastric fluid for Ritonavir Norvir tablets. So these are the three dots which is the observed data in simulated gastric fluid at pH 1.2. Ritonavir is a weak base. We initially used a default particle size of 10 micrometer, which is there in Simcyp. Since it's a weak base, it shows very high solubility in acidic pH. So when we ran the initial simulations, the red line is our simulated ones, and we were clearly over predicting what we observed in vitro. And you can argue that we don't know the particle size which is to be used, because the particle size of the API in commercial batches, which are usually used in vitro or in vivo studies, are rarely reported in literature. This kind of information is never mentioned in the literature. So we really don't know the initial particle size which we should use for dissolution modeling. You should not really depend on the default particle size. You need to probe this a bit further to understand that what particle size you should use. So what we did is we simulated few scenarios where we increase the particle size and see, okay, whether we can still capture this dissolution. So even with 100 micrometer, we were not able to capture this dissolutions. And if I further increase it to 500 micrometer, which is actually quite big particle size, um, I was still predicting this dissolution. So with this, what I'm meaning to say is that uh, you really need to probe your particle size, and you should not use the default particle size. So clearly, we know that the dissolution of ritonavir is not governed by the particle size, and we know from the previous paper that it is the polymer which is controlling the release of ritonavir. So what we did is we fitted a first order release constant, which takes into account this polymer mediated release. So this is an empirical way how we handle the polymer controlled release. So we fitted a first order release constant to this one with an input size of particle diameter of 10 micrometer. And this is the results which we got. Depending upon what input parameter you are using. So if you are using 100 micrometer, we got these parameters. But if you are using, if we use 10 micrometer and we got this parameter, and if we use 100 micrometer, you can end up with a different set of parameters, but it will still fit the data. So here, the fitting of KD depends on the initial particle size, and it really doesn't matter that which particle size you use, because you are ultimately fitting the data with KD. So we use this 10 micrometer to fit the data, this first order release function to take into account this polymer control release. And as I've mentioned previously, that the use of default particle size should be justified by modeling of in vitro experiments. And we use these parameters in our PBPK model. Okay, so once we had a bit of understanding about our in vitro dissolution, moved on to the pH shift experiments. So these are usually the experiments which are done in literature. So you can see that this is a static experiment. So these are usually pH shift experiments. So you have a gastric media, and then you add concentrated intestinal fluid. You immediately change the conditions and the drug gets precipitate. But this is quite certain. And then you have these dynamic experiments where you have a gastric chamber, you dissolve your drug, and then you transfer your drug to the intestinal chamber slowly with a first order transit rate, which is representative of average population. And you can see measure your drug concentration, which is either dissolved or precipitated within the intestinal media. But the results which we gather from these experiments, we should take that results actually with a pinch of salt. We should not believe them instantaneously, because these experiments are done in a closed compartment. So you need to understand also that in vivo there is an absorption compartment, and it has usually been reported that the extent of precipitation and supersaturation which is observed in these closed experiments, they are overestimated, overestimation of the in vivo scenario. So we have to also consider this absorption compartment, and actually the dynamic compartments where you are further removing the drug from the intestinal compartments are a bit more representative compared to the closed compartment experiments. So we need to be a bit more careful in this regard. So this is the empirical precipitation model which we used within Simcyp. This is a typical profile. So this is that the concentration is initially increasing and then decreasing with precipitation. And this is a typical profile which we observed in a dynamic experiment in a receiver compartment. And in this model, one of the important parameters is this critical supersaturation concentration. We define this critical supersaturation concentrations with critical supersaturation ratio. So there are three regions in this, and critical supersaturation ratio is nothing but critical supersaturation concentration divided by the equilibrium solubility of your compound. So if in a transfer experiments, you know that what is the highest concentration you can go before the precipitation starts, you can use that information to define a critical supersaturation ratio. So in region A, nothing precipitates. The precipitations only starts when your concentration hits the critical supersaturation concentration. So once you are in the region B, you can define a primary rate constant, a precipitation rate constant, sorry. And once it gets from region B to region C, you can define another primary rate constant. You can also have a single value for the entire process, but dividing them, but if in your experiment you see biphasic precipitation, you can use two different precipitation rate to capture that behavior. It just gives you, having two different precipitation rate gives you more flexibility to model the entire process. So this is the empirical precipitation model which we used while developing the Ritonavir, while understanding the Ritonavir precipitation. And this is some of the data which is recently published from Professor Dressman's lab. And you can see that this is the data in compendial fluid, so simulated gastric fluid and simulated intestinal fluid. And this is the data in bioelement media, so fasted gastric to fasted intestinal. And you can see here that as the drug is dissolving in the gastric media, and when it is being transferred from gastric to the intestinal media, it precipitates quite instantaneously. So there is an immediate precipitation happening. And the precipitate stays at its amorphous solubility limit. So this dotted gray one is the amorphous solubility line. And you can see that in dissolution, it stays at its amorphous solubility limit. So, and we also have seen in the previous slides that the induction time, nucleation induction time of ritonavir is around 300 minutes in FASIP. So actually during the entire duration of experiments, this was also observed here that it is staying at its amorphous solubility limit, which was quite interesting. The same observations were reported by Ellenberger et al. In 2018 in their paper. So how we parameterized our precipitation model. So we know that as soon as the drug is introduced into the intestinal media, it is precipitating and remaining at its amorphous limit. So what we did is, because we are simulating ritonavir as an amorphous drug, so here we specified CSR, which is the critical supersaturation ratio, as 1. So with that, what we mean is your critical supersaturation concentration is equal to your equilibrium solubility. So these two lines are actually merged in this model because we are simulating ritonavir as an amorphous form. So what we are saying to the system with these parameters is, okay, my critical supersaturation concentration is same as my equilibrium solubility. Once my drug concentration goes above equilibrium solubility, I have a very high rate of precipitation constant, which brings the drug back to its amorphous solubility, and a primary rate constant, which is a very low number, which keeps the drug at this line, so at this equilibrium solubility. So this is also what we observed in vitro, and when we use these parameters, we were able to capture the observed data. So this is the fitted data from the release profile, which we observed before. And with these precipitation parameters, we were able to capture the plateau region. So these are the parameters which we used in the PBPK model. Now moving on to modeling the permeability of ritonavir in the PBPK models. So we used mechanistic permeability model. This is a model which is based on the Sugano work, which was published in 2009. And this model gives us the ability to predict regional PEF depending upon the different morphology in each gut segment. So an important parameter for this model is P trans naught, which is the intrinsic permeability of the neutral species. And you can predict P trans naught either from log P, or you can calibrate P trans naught by a mechanistic modeling of in vitro CACO2 experiments. Now in SIVA 4, we have introduced a module where you can model your in vitro CACO2 experiments and can actually fit P trans naught to explain your in vitro CACO2 experiment. So you can derive this P trans naught via modeling of CACO2 experiment. Also be predicted from log P. And the model takes into account transcellular permeation. It also takes into account paracellular permeation, the permeability through the unstirred boundary layer. So once you have this information, we then scale the permeability from the knowledge of the morphology of the gastrointestinal tract. So we multiply this with uh, the surface area expansion, which is offered by villus, and also the plicae circularis, the fold expansion. And a very important assumption of this model is that this fraction unbound in the UBL term. So with this, what the model is assuming is that it is only the unbound fraction of the drug which is available for permeation. So it is only the unbound fraction of the drug which is going to permeate. So with unbound, it is only the free fraction of the drug which is going to permeate. This is an inherent assumption of the MacBeth model. Of course, the minimum input parameters which you need for this MacBeth is the compound type, the pK, and the log P, and you can predict or calibrate log P from CACO2 experiments, which are predicted from CACO2 experiments. This is quite an important assumptions, and I'm gonna discuss in a few slides that why we needed a MacBeth model and not a direct prediction of PEF from CACO2 in order to explain the food effects for ritonavir. So in this model for ritonavir, we used mechanistic permeability model, and the log P of ritonavir was used to predict regional pre-transnot. So this is another set of an interesting experiments which were done by Zhu et al. And what they did is they have a USB4 apparatus, which is a gastric compartment. So they dissolved the drug for 30 minutes in this compartment, and then they introduced the dissolved and the undissolved particles in this aqueous phase. So this aqueous phase they tested was fasted intestinal fluid as well as fed intestinal fluid. And they also have an absorptive compartment. So they also have an octanol phase. And what they observed is that the extent of partitioning was actually much more in the fasted state. So when the fasted media was there compared to the fed media. And they attributed these observations to two factors. So the first factors which they attributed is the effect of gastric pH on drug dissolution. So they said that since ritonavir is dissolving in fasted gastric, with a pH of 1.6, it will dissolve faster. You will have a more concentration gradient here when the drug is being transferred, and then the more drug will pass into the octanol phase. Whereas in fed gastric, whose pH is pH around 5, you will have low dissolution, and when you transfer it into the fed media, you have less concentration gradient and therefore less transferred. But if that what is happening, you should actually see a higher slope here for the fasted state. So the flux which is determined by the slope of the curve, the initial flux should be higher for the fasted, whereas you can see in this graph that from 0 to around 110 minutes, they have the same slope. So we believe that that's not the major factor in explaining the food effects. So the gastric dissolution for ritonavir is not that important. And this is because this is a set of experiments which were recently published from Patrick Augustine's lab from KU Leuven. And what they did is they did some pH shift experiments. So this is fasted and this is fasted plus PPI. So they administered a proton pump inhibitor. So the initial pH in the gastric stage was around 7 in this case and was around 2 in this case. You can see that, of course, the drug dissolved faster at a lower pH compared to at a higher pH, but it immediately precipitated to its amorphous solubility. And here also, if the drug is dissolved slower, but it immediately dissolves to its amorphous solubility. So if the site of absorption is duodenum or the small intestine, this plateau region should be the one which should be governing how much of the drug is being absorbed. And this is kind of similar. So you should not see a difference performance between fasted and fasted plus PPI because your concentration in the duodenum is kind of constant. And actually, they did observe this. So they also took duodenal aspirate samples from healthy volunteers. So they administered ritonavir 100 milligram to 5 healthy volunteers, and they take both stomach and duodenal aspirates. And you can see that in the duodenal aspirates, both fasted and fasted plus PPI were having nearly the same profiles. So what they observed in vitro was actually the observation in vivo as well. So if the pH in the stomach is important, then you should see differences in the duodenum as well, but you don't really see that. And that's why we believe that the pH in the stomach is not very important factor in governing the food effect, which is observed for ritonavir. And we also did a sensitivity analysis in our model where we varied the gastric pH from pH 1 to pH 7. So this is pH 1, which is from fasted, and pH 7 is the pH of fasted in the presence of an PPI, which is a proton pump inhibitor. And we observed that it's really not sensitive at all. So there is no sensitivity happening here. And that's why we believe that the pH of the stomach is not important in this case. Another factor which is important is this free fraction of drug or its permeation. And I think this is the main factor which is important in explaining the negative food effects. So you do see that, that the plateau region in the fed state is less than the plateau region in the fasted state. And the free fraction theory assumes that your drug is dissolved, gets partitioned to the bile micelles. Both free drug and the bile associated drug can diffuse in the unstirred boundary layer, but it is only the free drug which is available for absorption. So only the free drug can enter the enterocytes. And as you can see that in fed state, we have more of bile salts, so we have less free fraction compared to that of the fasted state. So the free fraction is much more in the fasted states, and this could explain the negative food effects which is observed for ritonavir. So that's why we used MacPef model, because as you can remember from the equation before, the MacPef model inherently takes into account the unbound fraction is available for absorption. So it takes into account this free fraction theory. And if you simply do an experiment, and if you simply use Calco2 predicted PEF for permeability, you won't be able to capture negative food effects because you are not really taking into account this free fraction mechanism into your permeability model. So it is also very important to select the right permeability model. And we were fortunate in this regard because we have this kind of an information from literature. So this helped us also in choosing the right permeability model. In addition, we also included the static viscosity model. So in most of our model, the compartments are considered well stirred. We had the viscosity value in different segments of the gastrointestinal tract for fasted and fed state. This is based on meta-analysis. And you can imagine that the viscosity is increased in the fed state. So the increased viscosity would have an effect on the drug dissolution and diffusion. So we use static viscosity model while developing this model. These are the distribution and metabolism related parameters. Ritonavir has a very complex pharmacokinetic profile. So we got a lot of data from Kodrikova et al. Paper. So we had the Vmax KM for CYP2D6, 3A4, and 3A5. We included that. We also had information about the renal clearance from this paper. So we also included that in the model. The VSS was around this. This is a paper about the ritonavir model, which was published in 2018 by O'Mara et al. From Novartis. So we use the same value in our model, and the fraction unbound is around 0.05. And these are the different parameters for mechanism-based inhibitions. These are all based on literature value. The induction parameters, we also included the induction parameters. And we calibrated these induction parameters, particularly Inmax with rifampicin as a calibrator compound. And we also had the competitive inhibition for CYP3A4 and 2D6 involved, as well as we also have PGP inhibition parameters. So the parameters for KI for 2D6 and the PGP, they were optimized in order to recover DDIs because the in vitro parameters were not predictive. but for CYP3A4 and 5, these were taken directly from the literature. I want to mention here that the compound file which we developed is quite extensively verified for CYP3A4 and 5 DDI. So it is verified for time-dependent inhibition of CYP3A4 and 3A5 DDI. However, if you want to use this file for 2D6 and PGP, this needs further verification. So this component of the model is not verified, and also the induction component of the model is not very verified. So the major verification was focused on the time-dependent inhibition of CYP3A4 and 5. So then we did some initial bottom-up simulation. So we now have a good understanding of the absorption components, and we then simulated the profiles. And what we observed is that we are having a huge overprediction of our clearance. So and this is good and bad at the same time. It was good because we were happy that with understanding of our biopharmaceutics experiments, our absorption phase till 4 hours is quite nicely captured. So we were quite surprised with this, that okay, we are really close to our absorption phase, so we are doing right by putting those kinds of an absorption parameters. And please remember that we don't have the intravenous data, so there are always parameter identifiability issues. But we had a good understanding how our formulation is behaving, and this of us gives us a confidence in our absorption parameters, because even with the bottom-up predictions, we were able to capture this absorption. So this really guided us to understand, okay, which parameters we need to look at. So absorption was quite good at 4 hours, and there can be two possible reasons for this over prediction. The first is this huge fraction absorbed from colon. Ritonavir is an immediate release product, and this is a possibility that for an immediate release product, majority of the absorption occurs from small intestine and not from colon. Colonic absorption is much more important for extended release products. So there is this huge overproduction is happening, which could lead to this overprediction of terminal profile. And another thing which could be that we are not really capturing the in vivo clearance correctly by the metabolic IVIVE. So maybe we are missing some component there. So as a first step, what we did is, because we know that, and also it is published in literature, we really don't understand clearly how the drug is being absorbed from the colon, because we don't have so much data from that part of the gastrointestinal. We have to understand that. There could also be binding happening in colon. That could be one of the things which may be happening. We don't really understand this, because of binding to the feces, which may be happening. And there are a lot of literature there's a lot of literature which has either reduced the fluid volume in the colon, or they have reduced the permeability in the colon in order to capture the terminal phase. So what we did as an initial instant is to use a colon absorption scalar to 0.1. So we reduce the absorption which is happening in colon. And when we did that, we of course improved a bit the pharmacokinetic profile. So you can see that this is getting much closer. Those the Cmax and Tmax are relatively captured well, but there is still two-folds over prediction of AUC with respect to the observed data. And this then pointed out, okay, there must be something which we are then missing in metabolic clearance. So we are really not capturing the clearance of this compound well. And when we went on to look into more detail, we know that it is a very strong inhibitor of CYP3A4 and 5. And we ran some multiple dose administration scenarios for 100 milligram ritonavir tablet. And what you can observe is here is that as soon as you administer ritonavir, even from the first dose onwards on day 1, so this is once a day administration, maximum inhibition of hepatic and gut CYP3A4 is around 4.77 for liver and around 7.59 for gut. So there is a huge inactivation happening for gut. Since CYP3A4 is the major enzyme involved in the metabolism of ritonavir, when it is inhibited to such an extent, there must be an additional pathway which takes over in clearing this drug. So when the CYP is inhibited, some other pathway should take over in clearing the drug. So what we did is, in order to account for that additional pathway, we optimized an additional clearance. And I'm going to show you why we think that this is the this is the reason, this is a reasonable assumption that there is another additional clearance mechanism in vivo which helps in clearing the ritonavir once hepatic CYP3A4 is inhibited. So we optimized this additional hepatic intrinsic clearance. So we did a sensitivity analysis and we found that this 75 microliter per minute per mg additional clearance was found to explain the observed data. So we were able to predict, we were able to fit or simulate the state profile of ritonavir following single dose administration of 100 milligram. And you can see it here is that this additional clearance mechanism is actually important. So on the graph A, there is no additional clearance. And you can see that as the ritonavir is administered, this is a time-dependent changes in the percentage fraction metabolized. And you can see that the contribution from CYP3A4 is going down. The contribution, as a result, the contribution is from renal clearance is increasing, but there is a limit to which the contribution from renal clearance could capture the clearance of ritonavir. So we were missing some component here. So when we added this additional clearance, you can see that this actually rises to a value of around 50%. So at a certain point in a simulation, your contribution, which is coming from additional clearance, is as high as 50%. So there is definitely some additional clearance which we needed to include in the model in order to capture the clearance. And it would be good that if we can generate some in vitro data to identify additional clearances mechanism for ritonavir, or maybe find some more robust values for CYP3A4 and 5. But in this model, we have to use an additional clearance mechanism. So just to show you this thing that we developed our model, we fitted our model from a single dose study, and prediction of a multiple dose study for a compound like ritonavir, which is a mechanism-based inhibitor, is not trivial. So prediction from single dose to multiple dose is not a trivial task. And when we applied the same model to predict two different studies, which is Greenwald et al. And Casera et al., we were very surprised that we were actually able to explain the multiple dose. So this actually gave us confidence that this optimization of additional clearance suggests that the fraction metabolized by CYP3A4, we are relatively well capturing that. So we are relatively well capturing the fraction metabolized by CYP3A4 and 5, because once on multiple administration, CYP3A4 is inhibited, this additional clearance takes over, which is clearing the drug. So the contribution of CYP3A4 and 5, the fraction metabolized by CYP3A4 and 5, is quite captured. And you can use these kinds of data in the absence of the information. So if you don't have the intravenous data, and if you don't know what is the fraction metabolized by CYP3A4, but we can gain some confidence if by developing a model for single dose, if we are able to capture for multiple dose, this gives us confidence that yes, the fraction metabolized by CYP3A4 could be rightly captured. So this really boosted our confidence in the model. And this is some of the luminal concentration data, which is determined from Patrick Augustin's lab. So they gave this 100 milligram tablet. And you can see that in the model, we are able to capture the variability which is observed in the stomach. There's this just one individual which showed a really bizarre profile, but most of the variability is being captured of what we were simulating. And this is the duodenal aspirate data, luminal data, and we were able to explain this data also relatively well. And this was quite good that we had some luminal concentration data to verify the model, which gives further confidence in the development of the ADAM model for ritonavir. So this is the food effect predictions. So we fitted this parameter with with the additional clearance was fitted with this data. So this was explained well, but we were also able to capture the negative food effect. So a decrease in Cmax and AUC was observed, and this is because of this free fraction increase, which is there in the fasted state but not in the fed state. We were able to capture the uh, uh, fasted and the fed state. So the two reasons which were attributed, and we just fitted a single dose data for fasted state, and we are able to explain multiple dose. We are able to explain the food effects. So this was quite good. And first is that you can see that the blue one are the PEF. So the PEF is higher in fasted and lower in fed. So there is a decrease in PEF, and this is coming from a reduction in the free fraction. In the fasted state, also the diffusion coefficient is really reduced. And the decrease in diffusion coefficient is because of also the increased viscosity of the drug, increased viscosity of the lumen in the gut. So this will have an effect on the diffusion coefficient of the drug. So this negative food effect is actually coming from both the free fraction as well as a decrease in the dissolution rate. And this is quite interesting actually to see that. And because we have used the MacPuff model, the MacPuff mechanistically takes into account this free fraction theory. Just to give you I'll quickly wrap it up now because I want to leave some time for discussions, and we are approaching towards the end. So just to give you a quick, because we not only developed this model, we also compared it with first author models, and we have these 5 models where we have model 1, which was a first author file, a model 2 where we have 2 different files, one specific for fasted and a fed state. Then we have the ADAM model, which we discussed, but corrected Vmax parameter for ICEF. Then the model 4 is again a first order, which is based on the fraction absorbed predicted by Adam, but with the corrected Vmax. And then the model 5 is same as model 3, but with a competitive Ki component. And these are the results of these analysis. And you can see that the model 5 was actually performing better, both for PK parameters and for DDI. So the model 5 was developed with the properties of biopharmaceutic experiments for immediate release tablet. But in all the DDIs which we used, the tablet was the other formulations of Ritonavir were also given. So they were also given soft gelatin capsules and the solution of Ritonavir. So in that case, but the model is developed from immediate release tablet. So what we did is, for simulating a capsule and a solution formulation, we used the option solution with precipitation. So we understand the precipitation parameter. So once the drug is dissolved, it should precipitate from solution and from tablet in a similar manner, because the precipitation is happening from solution. But the release rates and those kinds of things can be different between the two formulations. So for capsule and for solution formulation, we simulated it with solution with precipitation. So when we matched in each study, when we matched the type of formulation, you can see that there is a huge improvement in pharmacokinetic parameters. And this really shows you the importance of including formulation parameters of a purge-purificated drug in assessing the DDI. So you can really see that this is quite a good improvement which is happening in terms of exposure as well as in DDIs. So when we use the ADAM model with the study matched formulation, the predictions were quite good. This is just to show you a table. This will be published in an accompanying manuscript. And you can see that with capsule and with solution, we have used solution with precipitation option, but for a tablet, we have used immediate release. I'm going to quickly point out to this study, these two studies, where the dose was administered. So for administration of 600 milligram of the dose, what they did is they administered 6 capsules of 100 milligram. And when we simulated, and in this they administered 4 capsules of 100 milligrams. And when we simulated these studies with solution with precipitations, we were actually under predicting the Cmax and AUC. So what I did is I did use the solution formulation option, and with solution simulation option, what I mean is that keep the drug in solution for the entire duration of experiment. So there is no precipitation happening. And there is quite a possibility here because you are administering 100 milligram of the drug in 6 capsules, and these capsules usually have a lipid excipient. So you are administering huge amount of lipid excipients, and it is possible that the presence of lipid excipients in such a large amount can alter the precipitation behavior, and maybe the drug is not no more precipitating because you have a huge amount of excipient in these kinds of administration. But this is just a hypothesis at this moment. But this hypothesis is something which we can address in an in vitro experiment relatively easy. So if we do some transfer experiments where we administer 6 doses together and see that whether we get concentrations above the amorphous solubility, the component which is coming, the solubility enhancement which is coming from lipids. So this is something which we can be investigated, but this is quite an interesting observation. And these are the all DDIs which we have predicted. So we used around 18 studies where we verified the CYP3A4 component. And this is just to show you, this is my last slide, second last slide. And the blue and the red lines are the bioequivalence limits. So 0.8 to 1.25, and the orange and the green are the twofold. And A and B are the predicted Cmax and AUC, so the exposure. Most of our exposure were actually within the bioequivalence limit. So it was even a stringent criteria than the twofold. And even for the DDIs, our predicted Cmax and AUCs were within the, most of the studies were within the bioequivalence limit. So this was quite encouraging. So with this, I hope that I'm able to convince you that we need to model this in vitro biopharmaceutics experiments, and we can generate really good information from these experiments, which can help us to parameterize the absorption models. And this study really highlights that it is having a single model where you have both the biopharmaceutics and the DDI can be quite powerful. The compound file is available in version 19, so please feel free, have a look at the compound file and try to investigate it with your compounds and feed us back if you have any feedbacks. We would be really appreciating that. So just to conclude that some of the limitations is that the disintegration rate of the Norvir tablet in the fasted state is assumed to be the same as that of the fed state. So there is a lack of in vitro data of the disintegration rate of the tablet in the fed state. And you can imagine that because of the viscosity, the disintegration rate can differ. We can do some experiments here by mimicking the viscosity in the fed state by adding polymers like HPMC. But this requires some in vitro experiments. We use a static viscosity model, and we are working on dynamic viscosity models. You can imagine that the viscosity would not remain high throughout the duration of simulations. This is unrealistic, but we need to have more research done in this area as well. And finally, we need some experimental exploration of this additional metabolic pathways. So what we fitted is additional clearance. So additional data can be generated in that regard. We may be able to have bottom-up predictions. This is the team which was quite instrumental in getting this whole work together, particularly David and Masood. They were really helpful all the way. Thank you, and I'm ready to take your questions. I see some questions coming. Just wait a minute for a moment. Let me. Okay. Okay. There's some coming. Check my chat. Okay. I have a question here regarding auto inhibition. Can you implement direct auto inhibition and time dependent auto inhibition within the same compound file. The time-dependent offer inhibitions can be defined by K inact and K app. Let me go to the interaction-related parameters tab. I hope you can see my screen. So K app and K inact values were applied here with the mechanism-based inhibitions. I'm not really sure what do you mean by direct auto inhibition. Can you expand on that? Hello? KI, not time dependent. Oh, okay. So yes, of course. If you're talking about competitive inhibition, we can include that as well. So if it is a competitive inhibition, then you can, or a non-competitive inhibition, you can include that component. Actually, in the model, we include this KI competitive inhibition directly as well. So both of these are included in the model, the competitive inhibition as well as the mechanism-based inhibition. Okay, thank you. Please feel free to unmute, and we can also have a talk if you like. We have some time left. Can you calculate how to calculate that? Yeah, please go ahead.
Excuse me. This
Yes.
is Yoshikato speaking.
Yes.
And can I have some questions?
Yes, I can hear you well.
Yeah, thank you so much. And I have some question about the permeability change from flaccid and fin state.
Yeah.
And I understand the one of the reason for the negative food effect of this compound is the permeability change from flaccid and fin state, and also the viscosity. And so, in my understanding is correct, probably the permeability change will be the occurred for some compound, but how do you think for all compound permeability change will be occurred or not? And which property will be the one of the important factor?
Okay. So if I understand your question correctly, you are asking that what is the for what compounds the permeability change would be negative, or for what it won't have an effect. Is that correct?
Yes, thank you.
Okay. Okay, so let me go to the slides of this permeability so that we can have a bit of discussion there. So of course it depends. It's an interplay of so many factors. If your compound has a good affinity towards bile salts, if the rate of association of your compound to the bile salts is more than the rate of dissociation from the bile salts, then you should see a negative food effect because your compounds like to stay within the bile salt. But in this model, we assumed as an instantaneous um, uh, equilibration between bile salt and the aqueous media. But you also have to consider that these bile salts and your drug is also transiting into the is also transiting uh, between one segment and another. So if your drug is highly bound in duodenum or in jejunum 1, which is the site of absorption for a particular compound, and if it is transited from that place because it is bound to biles, then it won't be absorbed. And you can actually see that in here. If I show you the, so you can see this in this one that for this compound, majority of the drug is absorbed from duodenum and jejunum 1, where we actually see a decrease in permeability because the drug is also transiting. But you don't see a very big difference in permeability in other segments. The full colon, you really don't see that. And even in jejunum 2, you don't see that. But this effect was much more prominent in duodenum and jejunum 1. And you can see that the fraction absorbed was actually decreased. But it's also the viscosity as well, because the viscosity changes are prominent in duodenum and jejunum 1, whereas the viscosity of the other tracks less similar to that of the fasted. Combination of various factors But if you have some measurements of your association of your drug with the bile salts, then you can get more understanding that how fast and how quickly your drug is associating with the bile salts. I would assume that if your drug is highly lipophilic, it should partition more into the biles and it would like to stay in the bile. So for really highly lipophilic compounds, you should observe this association with the bile. But again, it is really a lot of factors.
Samit, I just add a bit more on that one. As Samit said, there are interplay of different parameters. So the methylation is increase your solubility. So if you remember the equation that Samit showed, as a result of bind salt, you are increasing the solubility. But on the other side, the permeability, it may reduce for the reason that Samit just explained. So there is a balance on how much solubility is going to go home and how much permeability is going to be hindered. So in some cases, you may see that negative food effect. In some cases, you may not see it. So you have to, unless you consider all of these together, you won't be able to appreciate or model those.
Yeah, thank you, Masood, for that comment. And I just want to quickly mention here that if you are not using the MacPef model, and if you directly use a PEF, which is predicted from CACO2, then you don't have this free fraction effect. So if I do the same simulations with a CACO2 permeability model, I was actually predicting a positive food effect because my solubility is increased. But as Masood said, that you need to take into account this free fraction theory as well as this increased in solubility, so as to understand that which factor or which parameter is predominating.
Okay, thank you. Thank you. Thank you so much.
Okay. I got a question that can you explain how to calculate KSP parameters? And I would like to know when we need to use it instead of a solubility factor. Okay, that's a really good question, Wakayama. So you can calculate your KSP parameter is the solubility product of of your salt. So the main species as well as the ion, and it is usually be determined at the pH max. So as for instance, let's consider an example of a weak base. So as you are going into the acidic range, you are start observing a plateau in the acidic range, and you can determine the solubility limit at that pH max. With the calculation of KSP, so there are equations there, and depending upon the salt type, so if it is a salt of weak acid and a strong base, so if it is 1:1 salt or it is 1:2 salt, depending upon the salt stoichiometry, the equations are different. How you can calculate KSP, but we are providing this estimation of KSP in SIVA 5. So SIVA 5 is scheduled to release somewhere in later this year, because we have this KSP model within Simcyp, but we want to provide an in vitro tools where you can estimate KSP. But depending upon the stoichiometric ratio and the kind of the salts which are forming, the equations are different, and you need to take into account those stoichiometries in order to calculate KSP. And another question of you is that when you want to use this KSP model more and not the solubility factor. So there is an interesting example for haloperidol. And for haloperidol, what you observe is as you go down in the pH range, you actually start observing a decrease in solubility. So you increase as you go to the aqueous, then you reach a plateau region, and then you actually go down. And this is happening because of the common ion effect, because you are adding more and more hydrochloride in order to lower the pH, and hydroperidol hydrochloride salt is formed. So you are adding more chloride salt, so it is precipitating the hydrochloride out. So this is the common ion effect which is happening. So I would assume that if you have a salt API, and if your salt API is a hydrochloride salt, you can expect to observe a common ion effect in stomach. So when you administer that within stomach, the content, based on the meta-analysis which we did, we found out that the chloride content in the stomach is actually quite high, and it is in a range which can cause this common ion effect. So I would particularly be careful And I would be interested in understanding that whether I am observing any common ion effect when I'm administering a hydrochloride salt. So in that case, yes, I would prefer to go with a solubility product model rather than a solubility factor, because solubility factor just will keep your drug at the at a plateau region. It won't take into account this common ion effect. I hope that helps.
Thank you. Thank you for your explanation. That makes me clear.
Okay, that's great. If there are any more questions, I would be happy to take some. Otherwise, please feel free to drop it to us on our email ID. And if you want to know more about this work, or please just let us know and drop us any questions you have. Okay. Since I am not seeing any more questions via chat or via the audio, I would like to thank all of you for taking this time for listening to us, and please feel free to send your questions. Thank you, everyone.